Welcome back to this session. I'm Terry Utlat. I'm a steering committee member, and I also work for Intel Corporation. We're going to listen to Heath Rushing and Andrew Carl today from Adsergo Consulting Company, and they're going to be talking about text mining. If you looked at their abstract, they claim or make a statement that about 80% of information stored by companies is stored in text format. So they're going to show us how to incorporate text mining using R and JSL. So.
Yeah, thanks a lot, Terry. I'm just going to do a brief introduction, then I'm going to let Andrew take it away. And John Saul this morning, if anyone was listening, right, is he brought up a data set and he said, wow, look, we have a text field. I think a lot of people want to start doing stuff with text fields, right? Did you say that, John? And he showed the word count, and I just kind of smiled and looked over at both Andrew and Jim and just kind of smiled and said, imagine that. And how this came about was we were working with customers in terms of DOE and reliability, a lot in the Department of Defense. And we'd constantly get questions about, well, we do have pilot comments, but we can't do anything with this. And they would say, it's not like that we're doing this every day, right? It is things that we're doing maybe once a month or once every few months. We're seeing the same thing with maintenance reports. We're seeing the same thing with depots. These are people that were not going to be not something like SAS Enterprise Miner, text miner users. They were engineers, they were test engineers, they were reliability engineers. They needed a tool to supplement all the other kind of analysis that they had going on. Okay, and that's how this came about, where Andrew and I were sitting at lunch one day and he had done some work with R and text miner, and I just said, it sure would be nice if we could bring all that into to JMP and to be able to really take advantage of all the rich analysis techniques and the graphical tools that JMP has. And so we started working on this and really started presenting it to a few people and started getting feedback. With that being said, we're here all week. I'm glad this is the first day. If you have feedback, we have a basic tool. We have had feedback from a few customers that said, it'd be really nice if you had this and this, okay? And that's something that we're looking for from you. If you want to walk up to me and say, it'd be really nice if that tool had this, all right? A lot of this is customizable that you will see him present. Last thing I'll say is this, is a good friend of mine, Terry Woodfield, and I were having a conversation. He is a SAS instructor, and Terry and I were talking about all the theory behind text mining. And he put up he drew on a piece of paper, he drew a box, and he said, hey, this is text, and this is analytics, and something happens in between here. And I said, yes, Terry, I know, but how do you explain that in a very short period of time? And he said, just look out and say, a miracle happens, okay? All right, and then so we are not going to focus on theory today. We want to show you, demonstrate the capability of the interaction between R and JMP and the different things that we found that you can do. You will hear a few terms. Some terms, Andrew will talk about start list and stop list. Some terms he'll just say, this is called singular value decomposition, and this is how we get to the analysis, right? We're very, we can give you references, or talk to you about, the theory behind that. We're gonna focus on the demonstration. Sound good? It's your show, my man, take it away.
Thank you very much, Heath. And thank you everybody for coming too. I'd like to first point out what our major application is going to be. We're first going to look at a couple small examples to illustrate what the script is doing. And then we're going to look at NTSB airplane accident reports, NTSB being National Transportation Safety Board. And you can get this data from the textbook reference at the bottom, text mining, predictive methods for analyzing unstructured information. And we're going to look at how we can extract numerical indices to represent the text, and then, using JMP, use both supervised and unsupervised learning methods on those numerical indices. So first, let's take a look at the first 8 documents from that NTSB example. So these are a few sentences in this column, narrative cause, that summarize whatever caused this airplane accident. So the first step in text mining, and what's typically used as a so-called bag of words approach, where we don't worry about the ordering of the words or the syntax of the grammatical syntax of the words. We extract what's called a document term matrix. So each document is represented by a single row. Each word that appears in the entire collection of documents is its own column. Now, there are a couple things to notice about the words that appear in the columns. First of all, notice the word adequate, or what it looks like it should be adequate, has been chopped off. So this is a process called stemming. Stemming consolidates singular and plural versions of nouns and conjugated versions of verbs. So even though they might appear in different grammatical context in the sentence, in the documents, it's the same idea. So we consolidate those through stemming. Another issue, so notice that the first word of the first 5 documents is the word the. Words like the that appear in virtually every document don't give us any discriminating power between the documents. So we take those out. Those are called stop words. And so if we scroll over to the right, we can see that the word the does not appear at all in the list of words. So there are some other processing options we'll see when we bring up the script interface. The main issue, we can't do this for very large applications. We can't just do this and then either in JMP or send this back to JMP, because this document term matrix grows so large that it's not even a processing problem, it's a memory problem. However, it's kind of hinted at by this example, this matrix is almost always very sparse. And so if you have the capacity for sparse matrix algebra, you can store this matrix as a sparse matrix and then also perform algebra on it, which is great for R, but we can't do that in JMP. So what do? A common method for text mining is to perform a singular value decomposition on the document term matrix, which just is a method of a rank reduced singular value decomposition, which is a method of rank reduction, dimensionality reduction. And so we can reduce those 68 terms to, for example, 3 columns. And these columns are dense, but we can reduce it, even for an application with 15,000 words, we can reduce it to maybe 100 or 2 singular vectors. And these preserve as much information as possible. So now you see we've got text and then numerical representation of the text, which we can then perform clustering on. We can also cluster terms, and we can use these vectors as input to predictive models. So the fit model platform, the neural platform. Another interesting feature about this singular value decomposition is it helps us take care of synonyms. And so let me show that in an example. So here's another very small example, and it's small so we can see what's happening. So look at the first 12 entries. They're all some variation of the soda machine stole my money. And also I mixed up the ordering so you can see that the ordering of the words doesn't matter and that the punctuation doesn't matter, because we optionally can remove the punctuation. And then we have some of the unrelated information about the pilots at the airplane information at the bottom. So let's bring up and take a look at the script interface, and we'll run it and see what it does with this. So I tried to blow up some of the text so you can read it better. So the first thing we do is we specify which column contains the text data to JMP. Optionally, if we have a column of stop words that we would like to include for JMP to take out, we can specify that. I don't have that here. Language, we need to specify a language for the stop words and the stemming. Right now, it supports English plus 10 other languages. And if you have some other language besides one of these, it can still process it just fine. You won't take out the stop words or stem the text. The frequency weighting, we're going to use the straightforward document frequency weighting, which is simply a count of the number of times each term appears in each document. You can put local or global weights on that, which sometimes gives better results. The other pre-processing options include removing punctuation, which we need to do this because otherwise the punctuation at the end of a sentence will be concatenated onto the last word of the sentence. We normalize the case, everything's lowercase because this is case sensitive. Remove numbers, we might not always want to do that if you're working with some text that might refer to part numbers or to different codes. You might want to leave those in. And we're going to remove the stop words and stem the text as we mentioned. The reduced strength of the SVD, is the singular value decomposition, refers to how many vectors we reduce the document term matrix to. We have limits on the word length, which are sometimes helpful. A lot of times words over a length of 20 are mostly going to be just run-ons that might not be useful. It's also often useful to remove terms that appear only in a few documents, especially if a term only appears in one document. That doesn't really give you any discriminating power to cluster documents or to look for patterns, and a lot of times those are just typos. So you can greatly reduce the dimensionality of your problem and also get rid of noise terms that way. We have the option to to return the document term matrix. But for large applications, you don't want to do that. You want the singular value decomposition. And then we have some output options that we'll take a look at after this when this runs. So I'm going to run this. And a note about the scalability of the program. This is a small example, and it's going to take a couple seconds to kick in R and to run. But a lot of that time is just the load up for R. I've run this on an example where I've got 10,000 emails with anywhere from a few sentences to several pages long, and that might run in approximately 5 minutes on my laptop. So it's pretty scalable. So a kind of highlight here. So some of the output options. So notice this, we have a list of the terms that appear, and then we have some indices now. So in addition to clustering terms, you can cluster, in addition to clustering documents together, you can cluster terms. Which terms appear together frequently or are related to each other. And what do I mean by related? So looking back at the example, so soda machine stole my money, pop machine, Coke machine. So these are all the same thing. Soda, pop, and Coke are just synonyms, okay? But notice soda, pop, and Coke don't appear together in any of the documents. But look what happens when we plot the first two singular vectors that are returned. And this is a reason we like to bring this into JMP instead of just doing this in R, because this wouldn't be so easy in R to manage these graphics. So soda, Coke, and pop are all mapped to the same point. So the singular value decomposition helps us recognize that those are synonyms. They're being used in exactly the same way, even though they don't appear together anywhere in the documents. Also notice that we have 2 dimensions. So the topics being the soda machine stealing your money, and then also this airplane stuff. So this decomposition helps you sort out the various topics that appear, the common themes that appear in your set of documents. Okay, so now let's take a look at the full set of NTSB data. So there are 3,000 reports in this example, and we extracted 300 singular vectors to summarize it. And let's take a look at the output. So the 2 most common themes that appear here, we see that engine loss of power. That's maybe not surprising. Then here we have a dimension for pilots failing to maintain control. So those are maybe the 2 most common themes associated with accidents. We can also, thanks to JMP's graphics features, we can plot that in 3D. If you want to look at the third factor, and I haven't blown up the text here, but the bottom word for the third singular vector is land. So issues involving landing. We also get, I'm sorry, I'm not good enough I tried to blow up the words here. I was able to increase the other text size, and the numbers increased in size, but the terms over here didn't. But we get a frequency count of the terms that appear across the entire collection of documents. And is common with text mining applications, you see a few terms that appear quite frequently, and then several terms that appear very infrequently, and that follows a lot of times what's called a zip distribution. So in addition to getting this count of the words, we can also summarize this with what's called a word cloud, which is an R graphic that R produces it, and then we send it over into, we import it into JMP, and the words that appear in the middle and are largest are the ones that occur most frequently, and then as you go out, they occur less frequently. And so that sometimes gives a nicer visual summary of which words are occurring most frequently. So how can we use those indices that are returned Sorry, it's being a little slow. So first of all, we're going to cluster terms together. So this is a dendrogram for clustering on the vectors that are returned for the term clustering. And you can see the large green cluster is, and this happens quite a bit, is you'll have several terms that don't have much discriminating power. The decomposition didn't find them very useful. And then you have fewer terms that are more useful, and some of those occur in clusters together. And see, I had a couple I want to point out. So for example, we look down here at 55. So a blocked nozzle screen. So the fuel to the engine is getting cut off. 114 glide path, which has something to do with landing. Heath is the Air Force guy, so ask him about the planes. Both Heath and Jim. And then also 129, I thought this was kind of interesting. Boat wake. I wouldn't have expected to see boat wake appearing in these accident reports. That's actually harder to read with the blue. But what the issue is the planes come in, these seaplanes come in and land, and then they don't see the boats, and they hit, and they kind of bounce and break down. So in addition to looking at kind of all of the terms together and looking for clusters, we can zero in if we have a particular term we're interested in, which terms occur most frequently with that term. And we have a couple options. The first on the left, where we have we're looking at the term oxygen. So which terms occur most frequently with oxygen? Using the vectors that are returned by the singular value decomposition, so on the left side, so in order cardiovascular, consciousness, hypoxia, so you're not getting enough oxygen, stroke, incapacitated. Actually, stroke doesn't appear at all with oxygen in these documents, but stroke occurs frequently also with consciousness, incapacitated, and cardiovascular. So again, this is the singular value decomposition kind of clustering synonyms together. You could alternatively use the cosine similarity, which requires the full document term matrix. So that's something you do in R, and then you could send this list back to JMP. And just the most common words occurring with the oxygen are hypoxia, incapacitated, without. So planes are flying up without supplemental oxygen, and then the pilots are passing out. So in addition to clustering on the terms, we can cluster the documents, which a lot of times this is the more interesting application. We see groups of similar documents, and we can either, so there are a couple reasons you might want to do this. One is kind of an exploratory thing. If you want to take a stratified sample of your collection of documents. So a lot of times you get a collection of documents, you're going to take some time and kind of read through a sample of documents. Or rather than taking a simple random sample of documents, if you've got 10,000 documents, but you're willing to take time to read through 100 of them if they're relatively short, you can cluster into 100 clusters, take a sample of one from each cluster, and that's going to be a more representative sample than just taking a simple random sample of all the documents. Alternatively, we might want to cluster for to measure association with another variable. In this instance, we have information about whether or not the accident was fatal. And so we want to see, are any of these clusters, do they tend to have more fatal accidents than others? So just looking at the frequencies of yes, no within each cluster, we see the cluster 188 has a total of 38 reports, but none of them are fatal. So that we might want to take a look at that one. At the other extreme, we have some clusters at the top. Cluster 205 has a total of 20 reports, of which 18 are fatal. So let's take a look at those. That cluster 205, which consists of fatal reports, if you read through, a common theme you see, the phrase spatial disorientation appears quite a bit. And you see mentions of VFC, which has to do with visual flight, VFR, which is visual flight rules. So people who are qualified to fly at daytime all of a sudden fly at nighttime or fly in bad weather and then get into an accident. Those tend to be fatal accidents. Another common, the next most dense cluster with fatal accidents, if you read through the reports, they all mention drugs or alcohol. So, which is kind of a self-induced spatial disorientation. And then in addition, so the third most dense cluster of fatal accidents is, you read through, you see the phrase failure to maintain airspeed, which can occur for several reasons, but that's a common theme through that cluster. So I guess the takeaway from that is if your pilot, you're going home and your pilot stumbles in drunk mentioning, he's bragging about how slow he's going to land the plane, you might not want to get on. So now let's look at the cluster of documents. So there are 38 documents here, and none of them are fatal. So is there a common theme? You read through and you see bounced landing in almost all of these. And it mentions improper, so it mentions also glide path and flare. So flares when they come in and then they pitch up at the last minute to have a nice soft landing. I guess they don't do that right. And then they bounce a little bit. So that tends to not be a fatal occurrence. And again, so this is like other retrospective studies, we're not making a causal statement here. But what this is good for, you've got this huge collection of data, and you can use this to inspire you for future experiments. Hopefully not a designed experiment in this case, but it can be informative for future studies. And then the second least fatal cluster, I mentioned soft terrain. So I'm not sure exactly what's going on, but something involving soft terrain. And so just as we can focus in on a single term, we can focus in on a single document. And you might want to do this if you've got this large collection of documents. Say you're doing an audit and you've got an email and you want to see, is there a similar email to this? Or you've got some unique plane accident and you want to say, did something similar to this happen? Well, what you can do is you can, and the way I'm getting these distances is I'm running the cluster platform, and then I'm saving the distance matrix, and I'm just sorting in the column corresponding to that document. So in this case, we have a crash due to the crankshaft fails, and then the propeller separates and hits the flight controls and the plane goes down. The most similar documents to that all involve propeller strikes, loss of engine power due to engine crankshaft. So it's picking up on the crankshaft and propeller. It turns out that there aren't any documents exactly like that first one, but we're still picking up the most similar ones to that one. I'd also like to point out that we can use, let me go back to that table. So these, we can use these singular vectors as continuous inputs to a model, and we can run, for example, logistic regression to test for whether or not which of these vectors are contributing to whether or not the accident is fatal. So we're trying to predict whether or not an accident was fatal. And by the way, this column does not say there were fatalities. Some of the columns do, but this column we're using doesn't. That would be kind of cheating, and you'd hope to do pretty well there. But this one doesn't, and we can see we held out some validation data, and you've got an accuracy rate of 89% and precision recall are both over 0.5. So, and you can use this either by itself to form a model, or you can use this to supplement other structured data. So you have other structured columns. You can use those columns along with these indices returned by this script to produce predictive models. And I think that actually does it. I wanted to save some time for questions. Are there any questions? It's okay. They asked me to repeat the questions for the microphone too, so.
Already done this, but I'd just be curious to see the code. Do you have the code up there?
Well, yes, I do have the code.
Are you allowed to show it, or is it?
He can show the code.
Okay.
What's that?
She said, "Do you have the code?" You talking about just the script?
Okay, can I just see the code? I'm not a JSL person.
The script?
So the script.
The script?
Yeah,
So the script?
Yeah, just show the script.
Okay. So I'm embarrassed. It's kind of like I wasn't expecting to have my code inspected. So it's not commented, it's sloppy. It's okay. So it's very, very messy, very messy. So at the top is just there's the structure for the interface, and this is all jump stuff. But where we get into the R stuff, so all the stuff in purple is we submit these R expressions, and this is where this is the engine of the problem is this R stuff, and you don't see the R. You don't have to do it. You don't have to know R. Jump calls it. So that's the scrolling down. That's the pretty sloppy. I'm embarrassed to show that. Another question.
Next question. What R packages do you use? There's a bunch of them, right?
Yeah, the main one is the TM package for text mining. The matrix package is essential for the sparse matrix algebra. There's one called IRLBA, which I use for because when you do the singular value decomposition, you don't want to do the whole thing. You only want to do it up to the number of vectors you want. And it's actually an approximation of it. Here, let me go up to the packages. IRLBA. And then the word cloud package gives the word cloud, and then RSTEM, capital RSTEM, does the is what we use for the stemmer. Because the TM package, there's some issues with the stemmer non-Unix platforms.
A question about when you do that for documents. Are you first of all preparing the documents as being a column in JMP, or?
So, that's right. So that's not absolutely essential. That's just the way I've got it set up right now. You can also do it. You can import from a folder. You can convert PDFs to plain text. But if you can specify a folder with documents, that's not in the script right now. But that's something we've been doing. It's just this was a kind of a convenient way to demonstrate the rest of the functionality. So oh, I'm sorry, I forgot to repeat the questions. So the question is, doing this process, and do you do that in R or do you do that in JMP? Most of the time I've been doing that in R, so in the conversion to PDF, I don't know of any functionality like that in JMP. I could just be ignorant of that. But actually what I've been doing is there's some GNU, some open source thing that I just run a DOS command on the folder and convert it, and it spits out a folder of text files. And then there's an option within R to specify a path. So you could set up the script, so you specify a path to the script, and then it goes to that folder and then pulls in everything there. So we can do that in JMP, but yes?
How far have you been able to push the R text mining capabilities? Are you able to do things like text mining using things like the LDA, the latent direct collect models, or is it still the very, I mean, I'm trying to see, right, in terms of JMP, do you use R for all the heavy processing?
Yes. Yes.
And is it possible to bring some of that back into JMP so it could be integrated?
So it's absolutely important. It's essential to have the sparse matrix algebra capabilities. JMP doesn't have that, so we have to. That's why we produce the singular value decomposition, send that back to JMP, and then JMP's doing the clustering, JMP's doing the fitting the models. So once it has those, then JMP's doing the lifting there. But the process of chopping up the text into a document term matrix and then reducing that document term matrix, that all, right now I don't know of any way to do that in JMP without the sparse matrix algebra.
And is there a lot of supervised learning that you've done here where you've got target keywords and you're looking for text phrases that map to keywords, or is it predominantly
so unsupervised learning too? Yeah, so that's what, when I had the dendrogram, so I was clustering on both terms and documents. And you could add also, once you do that, you could add other continuous factors in there as well if you wanted to look at clusters for, like in this case, if you had temperature or something like that, if you're wanting to cluster, add that to your cluster, you could do that too. So once you get those vectors back into JMP, they're fair game to treat as any other continuous factor.
Think about if you had a cluster, this is something that we really didn't touch on, and we have the capability to do this now, but think about if you had a cluster and you wanted to know all of your structured data. You know, it's like, why did it cluster in that way? And then you could very easily just do a cart, straight through JMP, right? I mean, you could do a classification regression tree on that to try to find out, is like, why did it cluster the documents in this way? You know, any of the structured data tell me, like, why did it do this in this way? A perfect example of that is we're looking at some, this was a long time ago in different, we brought all this into JMP. We were looking at economic data from different countries, and trying to find out why did it cluster in this way. We just ran a cart and we were able to come up with, hey, there was like unemployment of males under the age of 18 is a really big indicator of how countries cluster together. Okay. Yeah. I think there's something else here. It's pretty funny if you read the story on this NTSB data. Andrew, how long do you think if someone had this in their hands that they could come up with some of the conclusions you just came up with if they had the program?
From start to finish with this program?
Yeah.
Once you're familiar with the program, just a matter of running this and looking for these similarities, it's a matter of reading through, in an hour you can come up with, depending on how thoroughly you want to read through some of the representative clusters of documents.
Does anyone know the story behind this? That Congress has spent them a few months to come up with the same conclusions that he was just saying? Right? So if you look at the story behind this particular data set is, it took Congress like 2 to 3 months and they came up with a report, things like pilots landing at night were fatal, oxygen Things that were not fatal was another thing that you could have seen in those documents were student landings, right? Whenever they're with another pilot, those are the ones that weren't fatal. The other thing that we could do here is with the structured data is look at time of year. If we kept going with this, as you would see the time of year, for some odd reason, in Dallas in the summertime and in the Northeast and in the North in the wintertime, you see a lot more fatal accidents and you see these documents. Right? Anyone ever fly through Dallas in the summertime? Doesn't rain ever, does it? No, okay.
Any other questions?
I have a question about the data. So these are technical comments written by kind of a technical user. Do you guys have any experience or any feel for how well you would be able to accomplish this using non-technical audiences writing about things they don't know?
So the text comes from non-technical, so even like online comments to reviews and stuff like that.
That's kind of an extreme example, but yeah, that sort of thing.
Okay. Well, yeah. So it works. It's the same. It's the same process, and you can. There's a very wide text mining literature. So we followed existing text mining ideas in doing this, and so that'll bring out common themes. The same textbook has an example where they do online reviews for cars, and it's interesting to see the things in a fast amount of time. You can see themes that are coming out. So common complaints associated with brands of cars. What brands of cars are mostly associated with negative sentiments or positive sentiments? So yes, it's just as well applicable there.
We've also looked at this, not in this particular script, but we looked at comments that we had someone that was looking at comments from IEDs. And I mean, that's what they were going to look at. And so then it was a tool that they were going to use. And what it was you had structured data from where did this happen, what time of year, and then comments from people that, soldiers on the ground writing different things, okay? And then, so yeah, issues, at that particular accident. And so, yeah.